It's fun.
Yes. Okay. So in order to get to our space filling curve, we need to do preliminary things. So the first thing we're going to talk about is review. We're going to recall metrics. And from metrics, we specifically are interested in this square metric. And then we want metric spaces. We're going to need Cauchy sequences. Cauchy sequences, we can get complete metric spaces. And from those, we're also going to develop a supreme metric. And once we get all this done, then we can talk about the curve. So as a means of review, a metric. And when you think of metric, think distance on a set x is a function that takes, we can call it d. We take 2 points and spit out a number having the following properties. That first, we need to have the distance is never negative. So distance between 2 points needs to be greater than equal to 0 for all points in space. And that the equality really only holds when the 2 points are exactly the same thing. So distance should be 0 if and only if it's the same exact point. Distance between 2 points is irrespective to like the order that you're looking at it in. So distance between x and y is the same as the different distance between y and x. And then last one we call the triangle inequality. Which basically says if I take the distance from 2 points and then add on the distance from the endpoint and onto some third point, that overall sum will always be greater than or equal to if I did a shortcut and just cut from x to z. And in the plane, as an example, if I have x, y, z, then this is d x, y. This is dy, z. And so this is always that overall distance is going to be greater than or equal to if I would just cut straight across. And then it has to be equal to, because if we drop it all on the same plane, then it'd just be equal. And since it looks like a triangle, that's where we get triangle from. Doesn't have to be a triangle, of course, if you choose a different metric. But the analysis people got their fingers on some of these things, so. Okay, so the one that we're interested in for the space filling curve is the square metric. So given a vector in Rn, so say x1, and has n components to the vector, we define the square metric so a different way to think of distance, rho by the equation the distance in the square metric between two vectors x and y is going to be the max of x1 minus y1, and we check every single difference for the components. And we'll do an example of this. Because we're going to be doing specifically R2. So if I take two vectors in R2. That means they have two dimensions. So I can suppose, let's let x equal 0, 1, and y be 5, 5. So what I see then is the way this is labeled is the components of the x vector x1 and x2, and then the components of the y vector, and they have to be the same here. So I'll just say y1 and y2 are 5. And so I'm looking at this. Zero, 1. Our first vector is kind of small here. And then our other vector is 5, 5. Let's compare y. And so what does it mean to have distance between vectors? And so under the square metric, we're going to take that as the maximum of all these different things. So we need to compare. So our distance between x and y is the max of, and then each difference. So x1 minus y1. So the x1 we compare with this one, 0 minus 5. And then we do the next to x2, 1 minus 5. So we're just choosing of which one of these is larger, 5 or the 4. And that one's going to be 5. So we consider the distance, this idea of distance in a square metric between these two vectors, to be 5. And it's going to be, if we're comparing essentially the amount of which component has more distance away. So in this case, this is only 4. And this one is 5. And so we'll take the furthest possible way we can move away. That's our distance. Okay. As a means of review, if X is a topological space, then X is said to be metrizable if basically there exists a metric D on the set X that induces the topology of X. And then that's where we get a metric space. We say a metric space is then simply a metrizable space together with its metric, a specific metric B that gives the topology of X. So there can be different metric spaces with the same exact set, because you can have different metrics D that will induce different topologies. Okay, so now we can do Cauchy sequences. We've established at least enough language for these definitions. So we have XDB, a metric space. And the way we read that is basically, here's the set of objects. This is our notion of distance for this set of objects. And then we're saying that that actually induces a topology. A sequence, and we can just denote that by xn, so that would be like x0, x1, x2, x3, x4, etc. of points of the set X is said to be a Cauchy sequence. in the metric space if it has the property that's given a positive epsilon, then there is guaranteed to exist a sufficiently large integer n such that the distance between 2 points in the sequence x and xm will be less than the epsilon whenever those n and m exceed that sufficiently large n. And this we worked through in real analysis. So then we would say that the metric space is complete if every Cauchy sequence in X converges. There's just a brief lemma that we won't prove and then a brief theorem that we will prove. Here's the lemma. And it's that a metric space is complete if every Cauchy sequence in X has a convergent subsequence. And then what we'll prove that'll be helpful later is that Euclidean space Rk is complete in either of its usual metrics. The Euclidean metric D which basically that's the fancy way of saying how we normally conceptualize distance in space. And well, I should say or what we just defined, the square metric. A square metric problem. Okay. So we'll actually start with the square metric because it'll follow the Euclidean metric follows to show the metric space. So take the set Rk with square metric is complete. Let Xn be a Cauchy sequence in Rk. Oh, then set. So if I don't look at it as a sequence anymore, then I just take all of the parts of the sequence and turn them into elements of a set, is a bounded subset of the original metric space. For if we choose a sufficiently large n so that the distance in the square metric between xn and xm, if we make that less than or equal to 1 for all of the n and m that are past the large N, then the number, which we'll call m, which is just going to be the maximum value comparing the distance between x1 and the origin, and we'll compare everything with the origin up to xn minus 1, so the sufficient large N is the origin, and then once we actually get to n, we'll take that point in the sequence, and then we'll add 1 to it, because we'll get an upper bound for the distance between xn and the origin. So the points of the sequence all lie in the cube that we've kind of trapped it inside of from minus m to m, and then product with how many times we need. Since this cube is compact, the sequence, then our sequence has a convergent subsequence. We talked about that with compactness section. So our metric space, Rk with rho, is complete. And it's complete by the lemma that we didn't prove, but can't prove everything. And then we can basically since we're not going to use it, I won't flesh it out. But the way that you would then get from the square to Euclidean is that essentially you have sequences that are relative to rho and d only if their Cauchy sequences are relative. And then the sequences would converge relative to d only if it converges relative to rho. And then we can just copy and paste. I made it just in time for the fun pictures. Two more little things, and then we can actually start the topic. That if I have x and y as metric spaces, and then I take a map that x into y, I say that f is bounded if the image of the map is a bounded subset of the metric space that you're going into. So what we'll do is we'll denote this funny b with x and y to describe the set of all bounded functions. And then if we have a metric space yd, then one can define another metric on the set that we just defined. So the set of all bounded functions. Bounded functions from x to y. Find the equation. So I'll take rho, f, and g. So what we mean by distance between these functions is going to be the supremum of the distances comparing f of x and g of x at every single point in their domains. And so we see that rho is well defined with respect to the very first definition we did on metric. And here's the reason for the set. If I take the union of the images, then that is in itself bounded. If we have that the images themselves alone are bounded. And so we call this metric it's called the supremum metric. And then as a note of fourth a notational thing, we're going to call this script C with two metric spaces x, y to be the set of continuous maps. Fx. Okay. So now we can make our space filling curve now. It actually comes in the form of a theorem, which we claim. So if we let the capital I denote this interval, just the number 0 up to number 1, then there exists a continuous map that takes this interval into a square, unit square, whose image fills up the entire square. So the goal here is we're going to find a function that is going to essentially, when you draw it out, it in itself will be a two-dimensional space in the square. So like the idea is this is two-dimensional space, and usually when you think of like a function and you have some sort of a path going through it, and that's it's like one day it's a little counterintuitive to think that a path essentially could itself fill in the entire space. So there's lots of different ways you can fill in space. And we're going to use one that I am able to understand, because most of them are really hard. Step one is we shall construct the map F as the limit of a sequence. So limit of a sequence of continuous functions. Continuous functions Fn. So first, we need to describe a particular particular operation on paths, which will be used to generate the sequence of functions fn. So we'll begin with an arbitrary closed interval. Arbitrary closed interval from A to B in the real line, and an arbitrary square in the plane. With sides parallel to the axes, basically. So we don't want a weird square. We just want it to be nice and even with the axes. So with sides parallel to the coordinate axes. So we'll consider following path. If I want to convert this little interval from A to B through G, and then inside the square here, these tick marks are denoting these circles that I'm going to draw. We'll do like this little triangular path that goes like that. So that's a path that takes just this interval and then it puts it inside of the square. So we first see that it's going to be continuous. There's no break in that. It is a continuous path of our closed interval a, b into the square. And the operation that we're going to define, so the wish to describe replaces the path of G by the path, we'll call it G prime. And then here's what this will look like. So here's that interval length, right? A to B. And here's that center tick mark. But in between these now, I'm going to break these up into 3 smaller chunks. So then G prime is looking at that same square. But now what we're doing is we're saying, okay, let's divide it into equal parts. These points are still fixed, right? Because these are corresponding with the main ticks. But then now we have these other little dots that we're going to have in the centers. So we'll have a dot there in the middle, there in the middle, there in the middle, and there in the middle. And the way we'll connect it now is we'll do a triangle like that, a triangle like that, a triangle like that, and then a triangle like that. So this is what our operation looks like now. The operation that gets us from this to then more triangles, 4 more triangles. So it is made of 4 triangular points. Each half the size of G. Half the size of G. And the way you can see that is because G is technically going from all the way from here to here. And then now, when we split this in half, each one of these triangles is only taking half of that size. So we're shrinking it, scaling it down by half, and printing 4 versions connected together. And so we'll note that both G and G prime have the same initial point. Initial point and final point. So we're making sure this stays anchored down, and everything is just kind of adjusting as we expand. And then we can basically keep applying this over and over and over again. There's another way we can do it, and we can do it by corners adjacent to the square. So if I wanted to do, if I had some sort of a closed interval, and then through H, turn this into a path that's a triangle that's on the B sides of the square. So this is the bottom two. And we can do it like this as well. Boom, boom. Then applying our operation to the same exact interval will then give us that same square. And now I'm dividing into 4 equal pieces. That center piece is still going to be there. That's still the beginning point. That's still the ending point. And now what I've done is I've split it into multiple pieces. So I'm going to visit here first, and then go down here, and then go up here. So we could, I'll go there first, then there, another triangle. And then I actually need it there too. Triangle, triangle. So it's this, but rotated. And then these are gonna form the building blocks from which everything goes and blows up. Okay. Probably one of my more favorite operations I've ever seen. It's such a weird operation. Okay, so step 2 is now we define a sequence. And we've actually done the hard work for this for the most part. Of functions fn, that's I to r squared, so an interval in 2 squared. The first function which we'll call f naught for convenience. It wouldn't matter if we started with f1, we would just adjust the exponent later on in the proof. Is the triangular path that we drew for G originally. Path first drawn for G, and then we would be letting A be 0 and B be 1 for our unit interval. And then the next function after f0 is going to be f1. And this is the function obtained by applying the operation described in step 1. To the initial one. So essentially, we're describing what we drew for G prime. And then this is just going to keep going over and over and over. So next function after f1 is f2. And then is next function 2 is obtained by applying the same operation to each of the, but then it broke up into four things. So we'll apply that operation, but then for all of the pieces, to all four triangular paths that make up the previous one, which is that one, that make up. And if this is all a bunch of, I'll draw out all the progress of how it expands. You got F1. You can probably guess what's going to happen to F3 is we've done four triangular paths, and then every single one of those four turns into four more, so it blows up into another four more. So 4 times 4, there will be 16 times that we'll have to do for F3. So this just continues. And then I could describe, so I'll say, and so on, because this is a sequence. Let's see. At the general step, so now we're not looking at any specific F1 or F2 or anything, just Fn. The nth one, the nth time that we've made change the path is a path made up of 4 to the n triangular paths. Because every single time we did the operation, we multiply everything by 4, and just over and over and over again. Let's see, of the time considered in step 1. Each line in a square, and this will be important for later. And you'll see visually how the actual size of the squares that the triangular paths are in shrink and shrink and shrink. And so we can actually just say that the squares have an edge length of 1 over 2 to the n. So we keep having the length for every single time that we make a new do it again. And then if I wanted to get Fn plus 1, I would do the whole entire thing. I take all 4n of the triangle paths, multiply it again by 4, and I'd have 4 times 4 to the n plus 1. And then all of the side lengths of the squares would go in half again, so it'd be 1 to 2n plus 1. So I'll draw the sequence, basically, what we're describing. For the first two terms I can do by hand, and then it gets out of hand pretty quick. And again, the whole premise of this is we're finding something that's going to fill in this space. So I'll actually just redraw these even though we've technically seen them. So in terms of our 0 to 1, and then there's 1 halfway tick mark. And so now instead of calling that g, this is the first function in our sequence, f0. So that's where we take this. How do I want to fill in this square? Well, I start here, and there I only have one triangular path. The very first one. That's all. That didn't fill in the space very well. We've got a long way to go. So if I do the next one in the sequence, so then I'm looking at that middle tick mark, but then inside of each of these, I'm going to have, let's multiply those by 4. And so F1, I'm applying the operation. Here's my square again. Let's see how much space we actually fill. So cut it up, and I'm starting here, ending there. But now I've made it more complicated. I'm going to put triangle paths in the middle. So here's a mini triangle path, and then another mini triangle path, and then another mini triangle path, and then another mini triangle path. Okay, so did we fill up more space in the box? Yes, but we've got a long way to go. So this is going to keep going over and over and over again. not to scale. So it's one, two, three. Each one of these now has their own little pieces. And so if I'm going to iterate now, basically, if I zoomed in on just each of these dotted boxes, it looks like this. And then I just do it all over again. So I'm going to have to make the box a little bigger so it's easy to see. And then use different colors here. I'll use the blue to demarcate where we were. So if I were to split this just in half like that. But then on top of that, we're taking each one of these and splitting them into 4 pieces each. So then yeah. Because then now the path that's being drawn is all of these little mini triangles. So we're still starting here. We're still ending here. A lot more triangles going on in the middle. So we'll go triangle from here to here. And then from there to there. And then from there to there. And there to there. And so on and so forth. If you think this is tedious, just wait for the next one. Okay, so did we take up more of the space in the square? Yes. We're not done. There's still gaps. We haven't taken everything out. So I'll do one more just because it's hilarious. Zero to one. This one's to scale. This is the same distance as that, don't you know? So let's see if I can eyeball an even mark of 15. And then each one of these is babies. I'm beginning to understand why people use computers these days. Anyways, so, but now we can make the whole thing, and this is the last one look at because it just gets horrible. This is F3. And then now we'll map this interval and view it this way onto the same square again, drawn to scale. Exactly the same size. And since there's different layers to this, I'll do the overall grid, the first chunk in black, and break it down. This would be F1 level. And then F2 level. It's not perfect. Okay, so then the way that the operation is going to fill this space in is it's going to go like this. We'll do a copy of the first one, which is going to look like this. Then a sideways copy. and then another sideways copy, an upside down copy, a sideways copy, an upright copy, another upright copy, a sideways copy, and then that's halfway. Upright copy. Well, I keep doing the sideways copy when I say upright copy. Window. Wait, I was doing it. And now it's the upright version. And another upright version. From here. From there, upside down. Then from the upside down one sideways. There. Finally. There's the it's gonna fill the space. You can imagine this is only this is only three iterations into this. That's just gonna go up to unbounded levels. Like great.
The axolotl look nice. They look like an axolotl.
Then for you guys, what's about to be written down is just the technical jargon that talks about the pictures that are really nice. Okay. So it's not gonna be really anything new here. For the purposes of this proof, because we run out of symbols, we're gonna let the lowercase d, which is normally used for a different metric, but we'll let this one denote the square. Denote the square metric. Specifically, we'll restrict to the plane because that's what we're interested in. So the distance between two vectors be the maximum, just comparing the components. But we only have two pairs of components to do, like we did in the example. So then we can let our symbol rho denote the corresponding supremum metric on the set of continuous maps from I to I2, which will be rho fg is the supremum of distance f of t and g of t for t values in I. Now, because the unit square is closed in R2, it is complete in the square metric. Square metric. So then the set CII2 is complete in the metric flow. So we assert that the sequence of functions will take all of the fn's. So each one of these is each one of those pictures we drew, just increasing it. Defined in step 2 is a Cauchy sequence. Under the supremum metric. So to prove this, we require or we don't require that one, sorry. We examine what happens when we pass some fn to the next one, fn plus 1. Firstly, each of the small triangular paths that make up fn lies in a square of edge length 1 over 2 to the n, like we talked about. And the operation by which we obtain fn plus 1 replaces each such triangular path, by 4 triangular paths. That lie in the same exact square though. So there's going to be a natural subset bound in this here. So look at 4 in the square metric. Writing is really good. On I2, the distance between fn at some t and the next one, fn plus 1 t, is at most gonna be 1 over 2 to the n. There's no way you can get, if you're assigned the same box, essentially, that same subsection, it's not gonna escape it by increasing the precision. So as a result, the distance between fn and fn plus 1 is always going to be less than or equal to 1 over 2 to the n. And it follows that this sequence then is a Cauchy sequence. Since we see that distance for fn to fn plus m is going to be less than or equal to 1 over 2 to the n plus 1 over 2 to the n plus 1 up to n plus m minus 1, which is ultimately less than 2 over 2 to the n for all of our n and f. There's just one more step. Now that we've established that we have a sequence of paths and the paths are filling more and more space, the idea is that sequence, because it's Gaussian sequence, will converge. And since it'll converge to something, that means there's going to be some path that all of the paths are going to converge to. And that path should be filling up all of space. And the way we can say that it fills up the entire space is that it'll be impossible to choose a point inside of the square that isn't somewhere included along the path. Because CII2 is complete, the sequence Fn converges to a continuous function Fi I. So we prove that F is surjective. Just onto, that means its image will cover everything inside of the square. Let there be a point in the square, and now we will show that it's impossible that it has to then be in the image of this continuous map. We first note that if we're given some n, the path Fn comes within a distance of basically the which cell you capture it in, so 1/2 to the n of the part of the chosen point x. So for the path Fn touches each of the little squares of edge length 1/2 to the n, into which we have divided the square. So using this fact, we show that given a positive epsilon value, the epsilon neighborhood of our point intersects the image of the path. So we'll choose a sufficiently large n such that the distance for that sufficiently large n at f is less than half of epsilon. And then also we want 1/2 to the sufficiently large n being less than epsilon halves. This is the last bit here. So by the result of the previous paragraph, we will have the existence of some point t naught in I, such that the distance between our point and f at the sufficiently large n iterated path at t naught is going to be less than or equal to the edge length at that path. Then, since the distance between that with just the limit itself is less than epsilon halves for all points t in the interval, it follows that the distance between the point and our f of t naught is going to be less than epsilon, which is what we want. So the epsilon neighborhood of the point must intersect the image. And then it follows that our point is in the image, but I is compact. And since it's compact, its image is also compact. And since the image is compact, it is therefore closed. So it is therefore closed. And since it's closed, then the point's going to be included. And so we have the existence of the sequence that gives us those paths. We prove that that sequence of paths ends up being a Cauchy sequence. Being a Cauchy sequence tells us it converges to a continuous path, and then that continuous path includes every single point because it's impossible to pick a point that isn't on the path somewhere in the square. So we can fill space with a curve. That's it.
That'd be 3D. Hold on.